In this video we're going to revisit the idea of approximating a definite integral by using an approximation method. In the first section of the book, in the chapter, we looked at the right rectangular approximation method and the left rectangular approximation method. So in those two we were using rectangles to approximate an area under a curve, and what we're going to use here is a trapezoid to approximate the area. In general, this approximation method is a little bit more accurate, but also slightly more involved to find the value of. First, we'll have a look at the definition or the rules given for the trapezoid approximation method. To approximate the integral from a to b of f of x, remember this is finding an area between f of x and the x-axis. We can do that by using this formula where the interval is partitioned into n subintervals equal length, and we can find the width of each subinterval by taking the width of the entire interval and dividing by the number of rectangles. It's not immediately obvious why this formula works here. Note that the first y value is not being multiplied by anything, and the last y value is not being multiplied by anything, but every y value, every value of the function in between is being multiplied by 2. So what I want to do here is talk about the idea of the trapezoid rule and why it works and why it's useful to us. To start with, let's remember what this integral here means. We want to approximate the integral from a to b of f of x here, where f is the function given in red, and that integral is going to be given by the area between the x-axis and the function from a to b. So it's going to be this area right here, the area of this region. Now we want to approximate that area using trapezoids. So what we're going to do, and I'm going to use a large number of trapezoids here, or a small number of trapezoids, so a large width, just to demonstrate what we're doing here. But let's say we split this region up into 3 intervals of equal length. What we can do here is rather than use a rectangle where the left endpoint determines the height of the rectangle, or a rectangle where the right endpoint determines the height of the rectangle, we can use a trapezoid. And this is a trapezoid here because this vertical line and this vertical line are parallel to each other, and those two would be the bases. And so we can approximate the area on each subinterval by drawing in these trapezoids right here, essentially connecting the endpoints of the interval. So to find the area of this particular trapezoid, we would, and I'm going to label these here, y0, y1, y2, and y3. And those are, I labeled those in the wrong places. Those should be x0, x1, x2, and x3. And those are going to be the heights of each of the rectangles. So let me move those into the correct places here. So again, the y0, the y1, the y2, the y3, those are going to be the heights of these vertical lines here, and those are going to represent the bases. The width of each one of these intervals here we'll call h. We could call that delta x. It's also commonly referred to as delta x. So the area of this trapezoid then would be y0 plus y1 divided by 2 times h. And the area of the second one would be y1 plus y2 divided by 2 times h. And the area of the third trapezoid would be y2 plus y3 divided by 2 times h. That's just coming from the area formula for a trapezoid. Now we can approximate the area of this whole thing by adding all these together, and we'll notice that each one of them is being multiplied by h, and each one of them is being divided by 2. So we'll factor out that h over 2, and what we're left with is y0 plus y1 here plus y1 here, that would be plus 2 times y1 plus y2 here plus y2 here, so that would be plus 2 times y2 plus y3 here. And now it's becoming a little bit more apparent where that formula came from. If we were to have more rectangles here, the only difference is we would have more terms here in the middle, but our y0 would still only occur once, and our y3, or yn in this case, would only occur once. So the ones in between are being used for both the trapezoid to its left and the trapezoid to its right. So the area given by these trapezoids here is going to approximate the area of this curve. Generally, the trapezoid approximation method is more accurate than the LRAM or the RRAM, but it's not always the case. It just depends on what the function looks like. So let's do an example here. We want to approximate the value of the integral from 0 to 2 of x squared with respect to x using the trapezoid approximation method with 4 trapezoids. So the first thing I want to do here is I want to figure out the width of each interval. That will be given by h, and to do that we'll take the width of the entire interval and divide that by the number of trapezoids we want to use, and the width of each interval then is going to be 1/2. What we can do now is determine what x values we're going to be using. This will be split up into 4 intervals, which means we're actually going to have 5 x values. So our first x value we'll call x0 is going to be the left endpoint, that's 0. Our last endpoint, our last x value is going to be the right endpoint, that's going to be x4, and then we'll have x1, x2, and x3 in between. And since each interval has a width of 1/2, we're going to have 0.5, 1, and 1.5 for those x values. So just plugging in what we know into the formula for the trapezoid approximation method, we get that TAM4 is going to equal, it's going to be h divided by 2, so 1/2 divided by 2, times y0. Well, we're going to put 0 in for x here. Our function is going to be x squared, so y0 is going to be 0, plus 2 times y1. y1 we get by plugging 0.5 in for x squared, and it's going to be 2 times 0.25. And I'm going to give myself a little more room here. And then we'll do 2 plus y2, which comes from our x2 being plugged into our function. So it's going to be 2 times 1 plus 2 times y3. So we'll put 1.5 in for x squared, and we get 2.25. And then remember, our last one, our endpoint, is not going to be multiplied by 2, so we're just going to put 2 in for x squared, and we get 4 for that. And now just a simple calculation here. We can add all those together and divide it by 4 because we get 1/4 out front here. We're going to end up with 11/4, or 2.75. So what this tells us is this integral here, the area between the function x squared and the x-axis on the interval from 0 to 2 is going to be about 2.75. Now that's not an exact answer, but it is a more accurate answer than what we got when we did the same approximation when we used rectangles. So let's look at that real quick. If we were to approximate the integral from 0 to 2 of x squared, when we used RRAM, picture looked like this, and we got 3.75. When we used LRAM, we got a picture like this, and we got 1.75. And our trapezoid approximation method, we're going to get a picture that looks like this, and it's clear from the picture that we get an approximation that's a lot more accurate. This area right here that's shaded in looks a lot closer to the area between the curve and the axis than the LRAM and the RRAM did. And we can also see that our answer 2.75 is a lot closer to the exact answer of 8/3, or approximately 2.667, rounded to the nearest thousandth. if we look at a bigger picture of these, we can see why the trapezoid approximation method can be more accurate. We get extra areas sometimes in the rectangular approximation methods that are rather large. We get gaps sometimes in the rectangular approximation methods that are rather large. And with the trapezoid approximation method, those extra pieces and those gaps tend to be a lot smaller. They're still there. It's not immediately obvious, but we do have a little extra area there, and a little extra area there, and a little extra area there. So looking at the picture, we can see that we have a slight over approximation. We know the answer is going to be a little bit less than 2.75, but it's a lot closer than it was before. One other note about the trapezoidal rule: the trapezoid approximation method can be calculated fairly quickly if we've already done the left rectangular approximation and the right rectangular approximation method, because the trapezoid method is just the average of those two. So if we know the left and the right approximation methods, or we can compute those a little bit easier, then that might be an easier way to approach the trapezoid rule.